Here we have a projectile motion problem where we're looking at an airplane that's flying through the air. It's diving downwards. It's going to drop a radar decoy. Once the airplane drops the radar decoy, that decoy is then flying through the air. It's only under the effect of gravity, and thus it's an example of projectile motion. And we're looking at how far up the plane is, how far the decoy drops, how far the decoy travels as it's falling, and the time spent in the air. So we're given the fact that a certain airplane has a speed of 290 kilometers per hour and is diving at an angle of 30 degrees below the horizontal. What that's telling us is our initial velocity, which is as a vector. We'll have to deal with that a little bit later. We're told that the horizontal distance between the release point and the point where the decoy strikes the ground is 700 meters. So the horizontal distance between the release point and where it hits the ground, that right there is our 700 meters. From that, we want to find how long the decoy is in the air. That is asking us the time that the decoy is in the air. Recall that time is the same for horizontal and vertical motion. And we're asked how high was the release point, which is asking us what the motion was in the y direction. If we end up at the ground, we want to know how high we were. That is our y displacement that we're looking to find. So what we want to do here, if this is projectile motion, the decoy is flying through the air with no other influence other than gravity, then it's a constant acceleration system, and we can use the constant acceleration equations. We'll have two independent sets in the x and y directions. So we're told that the velocity initially is 290 kilometers per hour, and it's being launched at 30 degrees below the horizontal. So a couple things that we notice here. Number one, kilometers per hour is not our standard units, and so we need to use a conversion to be able to compare our velocity to any other amount. So we'll take 290 kilometers per hour. We will times by 1 kilometer is 1,000 meters, and we will times by the fact that 1 hour is 60 minutes, which is 60 seconds, which gives you a factor of 3,600 seconds, and thus we are traveling at 80.6 meters per second. We're also told that we are 30 degrees below the horizontal. So we can consider that, number one, as a negative 30 degrees. If we want to consider that a clockwise rotation from directly to the right, which is our constant, which is our reference point is the positive x-axis, we can think of this as negative 30 downwards, or we can consider it as a positive 30 degrees, and we have to keep in mind the fact that our x component of velocity will be negative because it's going downward. I beg your pardon. The y component of our initial velocity will be downward because it's headed, or it will be negative because it's going downwards. Either way we want to do it will be fine. So what that tells us is that the initial velocity in the x direction is the initial velocity cosine theta. So that is 80.6 cosine of negative 30 degrees. Which is 69.8 meters per second in the x direction. That's a positive amount because from our picture we just looked at, that is it is to the right, and so it should be positive in the x direction. If we look at the velocity in the y direction, that should be v naught sine theta. Here here that is an 80.6 sine of negative 30 degrees, which gives us a negative 40.3 meters per second. And so that is our initial velocity. And now we look at our kinematic equations. In the x direction, the acceleration is 0, because this is projectile motion, and thus we really only have a displacement in x, an initial velocity in the x direction, which is your velocity all along, and the time. In the y direction, your acceleration in the y direction is negative 9.8. That's always the case for projectile motion on Earth. And then we have a displacement in the y direction, we have a time travel in the y direction, we have an initial velocity in the y direction, and we have a final velocity in the y direction. And what we know now is the initial velocities. We just found those. They are 69.8 meters per second in the x direction and negative 40.3 meters per second in the y direction. We just found that from the vector we're given. The initial speed of 290 kilometers per hour at an angle of negative 30 degrees. And we're told the horizontal distance between the release point and where it strikes the ground is 700 meters. So that is our x displacement. Now what we see here is we don't have enough information right now to say anything about the y direction. We need a third value in the y direction. In the x direction, however, because the acceleration is 0, the x direction reduces down to delta x is the velocity in the x direction times time. And so in this case, we do know the distance in the x direction, we do know the initial, we do know the velocity in the x direction, so we could find time, which happens to be the first thing that we're being asked. On top of that, once we know time from the x direction, that will give us the third kinematic variable for the y direction, and we'll be able to calculate other things in that direction. So right here we'll look at 700 meters is our displacement in the x direction, is equal to 69.8 meters per second times time. And we find that the time is 10 seconds that we're in the air. Now, if we're traveling for 10 seconds in the x direction in order to cover this horizontal distance, that means we must also have spent that same 10 seconds traveling in the y direction. So firstly, this 10 seconds is the solution to part A, how long the decoy was in the air. It also is one of our kinematic variables in the y direction. Because the second part is asking us how high was the release point, what is the displacement in the y direction. We only had 2 kinematic variables to begin with, now we have a third one, so we'll be able to find the displacement in the y direction. We don't know anything about how fast it was going when it hit the ground in the y direction, and so if we don't know it and we're not being asked about it, we'll ignore that. We'll want to pick the kinematic equation that uses these variables. And that kinematic equation is this one. We want to find delta y. We know the initial velocity in the y direction is a negative 40.3 meters per second. It's traveling at that speed for 10 seconds. Plus, we have a factor of 1/2. The acceleration in the y direction we know is negative 9.8, and it accelerates for 10 seconds. When we add all of this up, this tells us that our displacement in the y direction is a negative 893 meters. That means that over the course of the motion, we're going downward by 893 meters. We end up at the ground, so how high we were released, our release point, our initial Y value, we could say, would be a positive 893 meters. And that would be the solution to part B.